Okay, so we just got done talking about two series, and this is going to jump right back up where we left off, but we're going to be talking about what to do when our number of factors increases and those combinations, those treatment combinations, get so big so quickly that we have to do something to control our experimental error. So this happens a lot. Let's review before we get started, let's kind of review a little bit about some basic concepts, such as why do we use factorials? Well, factorials are really useful for giving us that ability, that capacity to figure out whether the factors are operating independently or if they interact in some way. That's the main reason we ever employ a factorial design. But when we have factorial designs where the number of factors gets very, very large, just think about the number of treatment combinations. So early when we were talking about factorial designs, I didn't point it out, but if you had 2 to the 10, you're going to jump into thousands of experimental levels. Okay, so even just having 10 factors, it's going to become unwieldy to be able to control all of those sources of interaction, nor do you have the time or patience to explore all of this. So we need to think about, in cases where we have large-scale factorial designs, we need to discuss how to appropriately confound certain two-way interactions to really focus our model, but also to control experimental error ultimately. So in particular, the factorial arrangement that we use in one of these 2 to the k two series models can be kind of manipulated to provide an effective blocking factor for the investigation of certain factor effects and to facilitate the analysis of certain factor effects. So you may already know, say you're a chemist, and you may already know I have certain interactions or certain effects in the model that I know I need to develop and have rigorous tests over. So you may actually want to block or confound the remaining levels of the experiment so that you can focus in on those. This will also help you with estimating that pure error. So this is strategic. It's not just a fix. It's actually a strategic move, okay? So we call this confounding. Confounding is an incomplete blocking method or technique for specifically almost all the time 2 to the k type designs, maybe 3 to the k. You may see that in the literature as well. We're going to discuss specifically just the confounding for 2 series, 2 to the k designs. So when we use confounding in a 2 series experiment, we're going to use blocks the size of 2 to the k minus j. Okay, so for example, we could have a 2 to the 4th experiment, and we could find 2 blocks of size 8, or 4 blocks of size 8, or 8 blocks of size 2 to confound. You as the experimenter, or you as the statistical consultant, it needs to help the experimenter figure out how you do that confounding. But all of those are possibilities out of a 2 to the 4 design. Make sure you understand that. Enumerate that all out, okay? Why size 8? Size 8 is 2 to the 3rd, right? Okay, so 2 blocks of size 8. 4 blocks of size 4, 2 to the 2nd. Or 8 blocks of size 2. Whoops, I got interrupted here. Let's go back. Well, bear with me here. I've got to go back to full screen mode. Oh. Okay. So we use confounding here to gain efficiency. Confounding as a technique is that it allows us to collect and isolate the inefficiency from factorial effects that are useless, so that we can gain efficiency on the remaining factorial effects. So you, as the experimenter or the consultant, may know which effects are going to be experimentally important and ones that will be tested directly. You would never throw those away and confound those effects using blocking. Instead, what you would do is you would focus on those and make sure that those are coded within your factorial design. But what you would do is you would find certain effects that are maybe less useful as a research hypothesis, or maybe unavoidable effects that are not experimentally meaningful, and kind of colloquially, as Gary says here, we throw those interactions under the bus in order to gain efficiencies, get better estimates for the effects we care about. So those interactions that get thrown under the bus, we don't estimate them at all. We accumulate them together. We use them to get better estimates of our, or better control that experimental error in the experiment, and have a better test for the estimates that we do want to focus on. Okay, and we say that these interactions are lost because they are confounded with block differences. So that's why we talked about, a 2 to the 4th experiment. You could use 2 blocks of size 8. Okay, you might confound or block one of those. Or you could use 4 of size 4, 2 to the 2nd. So this is part of the experimental design where you have to decide how to do that confounding, which things to block together, use block differences for your design. Okay, so we begin with 2 blocks, just to give you an applied example here. So we choose which effect is going to be confounded. This is called our defining contrast, that one where we know we want to confound or kind of throw that effect under the bus, so to say. Then we determine the plus minus pattern for that defining contrast. Then we put the factor level combinations that are pluses on the defining contrast in one block, and put the negatives in the second block. And that way it gets canceled out, so to say. Let's see this in action. Let me get on the next screen. So we have a 2 to the 4th in 2 blocks. So let's start at the very simplest case possible. This is from a different textbook, and you can take a look at it. It's the introductory notes for 2 to the k factorial designs. But here's a simple 2 to the 2. Okay, remember the negative and plus denote the low and high levels of your factor. So we have an A factor, the reactant concentration, and then the catalyst, the amount of catalyst. So we can have a low amount of the reactant concentration versus a high, or a low amount of the catalyst versus a high. So we've got first the grand mean, which is that 1 notation, or 0, 0 is the other notation. Then we gotta have 0, 1, 0, which would be A, or 0, 1, which would be B, or 1, 1, which is for the 2 high levels of A, B. So note those levels, make sure you understand where that comes from. We could, if we go to the next slide, we could talk about the replicates within this experiment in the following way. We have the case where it's negative, negative, or 0, 0, where A is low and B is low, and there's 3 replicates giving you a total of 80. Then high and low, again 3 replications, low, high, and high, high. So of course, in the last set of notes, what we would have done is go through and do all the testing and refinement. And we could have estimated each of these effects. Now notice the degrees of freedom is 1 for each of these. This is partly what we worked out together in class earlier in the week. And our error has 8 degrees of freedom out of the total. So sometimes it's useful to be able to block that error so that you can gain more precision in your estimates. Let's see. let's add a dimension. I wanted to kind of lay this out as we start talking about that confounding or incomplete blocking, okay? So here we've added a dimension, so we've added a factor C. Here's our design matrix. Notice that each of these have the appropriate high-low coding for our factors. Okay, so here we can talk about that we estimate each of those factors, like in the last set of notes. Main effect for A is all the positive coefficients for A minus all the negative for A. For B, positive minus negative. C, positive minus negative. Those interaction effects are going to just be the differences between the averages of the 4 runs that involve that interaction. Here it is laid out for 2 replicates per treatment combination. And here's the full factorial effect. This is the point I wanted to get to so that we could talk about how to fully think about the blocking. And I'm going to go back to our slides in just a second. I just regretted that in the book there's not really a full enumeration of this, and I wanted you to be able to see this and see where this comes from. Okay, so we built it up. We said first we have our simplest case possible, the 2 to the 2. Then we stepped it up and made it a 2 to the 3. And now here's our full table of the plus minus effects for our 2 to the 3 design. Okay, so for A, for example, we can go through and look at all the cases where A is positive, there, and there. Take the average, subtract off the average of the cases where it's negative. We've already seen that in the previous slides. Okay, so I'm going to take a screen. Well, I'll just leave this open, actually. Let's go back to our slides. So let's step this up now. So now we've got, go back to constructing the design. We choose our effect to be confounded. Here we call it our defining contrast, and then determine that pattern for the contrast. So I'm going to go back and do that for that 2 to the 3. Then I'm going to follow Gary's lead and do 2 to the 4. But I felt like as I was getting ready to do this that it was just too much too soon with regard to that blocking. So using this full design, take a moment and jot down how you would estimate the A-B-C interaction using this particular design. Pause the video. Okay, so remember to estimate any effect within one of these 2 to the K designs. We just take all the positive terms minus the negative. So notice, where are these terms positive alongside here? Well, first with the ABC, the C, the B, and the A. So you'd have the effect of first ABC, then A, B, and C separately. Then you subtract off the negative effects. So first the full grand mean, then AB, AC, BC. So that's how we'd estimate that particular effect. And what would we be applying the pluses and minuses to? Specifically those coefficients from the model. So we could think about blocking ABC, the effect ABC here, and A separate from B, separate from C, and making those all positive with regard to the ABC interaction. This could define our defining contrast for the use of blocks in this experiment. So then the negative block would be those remaining terms, the AB interaction, the AC interaction, the BC interaction, and the grand mean. So that comparison of if block 1 is the positive terms, this, and this, and block 2 is the negative terms, then the contrast required to estimate the interaction that